Okay, so in most of the current assignments, the inferential statistics review, the inferential statistics applications, and then the final practice, I group the problems together usually with a little header that says this is the type of thing we're exploring in this group. And in the review, there was a section that says use the t, and that means the t distribution. And in this case, that's for to get the right margin of error formula. And I just want to go over the difference between a normal and a t based on problem number 8. And I'm going to use a different set of numbers than I have here based on a question that was messaged to me earlier yesterday. So, so the point here is a t distribution versus a normal distribution. When do we use one or the other? So both the t and the normal are symmetric bell-shaped distributions, but the t tends to be a little wider than normal. And that's partially to, partially it accommodates the lack of information. So we use a t distribution for a couple of reasons. If we don't know the population standard deviation, we should use a t. And or if it's a small sample size. And the central limit theorem says to apply a normal distribution to inferential statistics like hypothesis tests and confidence intervals, then the sample size should be greater than 30. So a couple of instances where we use a normal distribution are if we do know the population standard deviation. So if it's clearly given as some bit of knowledge, we would use the normal, and we would also want the sample size to be greater than 30, is what the central limit theorem states. And other times we would use a normal distribution is for a proportion. So the central limit theorem mainly talks about means. So standard deviation generally goes with a mean. So talking about a mean here, but we could have a proportion. So if it's a proportion, we're also going to use the normal distribution. And then over here, for the t distribution, again, we're talking about means. Could be a confidence interval or a hypothesis test, but we don't know the standard deviation and or we have a small sample size, which means that the sample size is less than 30. Then we would use a t. We'll never use a t distribution for a proportion. Okay, so that we have kind of like 3 categories when we choose a distribution for a confidence interval or a hypothesis test. If we're talking about means and we don't know the population standard deviation and or we have a small sample size, we use the t distribution. If we know the population standard deviation and we're looking for something about a mean and the sample size is greater than 30, then we'll use a normal. Or if it's a proportion, we'll use a normal distribution. And I had made kind of a flow chart before and I posted it that kind of relates the same information just in a slightly different picture. So now let's take a look at the problem that I was asked about, number 8, and show the desktop again. So in this review section, problem 6 through 9, at the top it said, hey, use the t distribution. So that to find the margin of error, you got to use a t-score, the sample standard deviation, and the square root of the sample size. So there's a couple of things I could do with that data once I have it. So now I'm going to go over to a different version of this problem. And I had several students actually have a hard time with this one. Because what I would like to do with this data is I'd like to highlight it and put it in that bootstrap interval that we played with before. So if I copy that and I jump over to a new tab, and let's go to stat key. When we first started doing confidence intervals, we played over here. Now this problem specifically said use T above, but that was way above, and so sometimes we forgot about it. So I should be going here, but what happens if I try to do this instead, the confidence interval for a mean? And that was where we went in and threw our data in. I don't have a header column or header row at the top, so uncheck that. And so here's my sample. Mean is 44.664. Standard deviation of the sample is 16.211. We'll have to modify that in a minute, but in StatKey, I could just say, hey, generate thousands of similar samples. So I've got 7,000. This question asks for a 98% confidence interval, so 0.98. And so this says the confidence interval should be like 34-ish up to 55-ish. Unfortunately, that won't answer this question properly because we were asked to use a t-distribution for two reasons. The population standard deviation is not known, and it's a small sample size. So what I did is I just kind of thought about the problem, just the way we've done things historically from a few weeks back. At first, I'm ignoring what was said above this group of things, which says, hey, use the t-distribution. So this is just a similar example. Let me blow it up a little more. Oop, no, hang on. There we go. This is a similar confidence interval I did by bootstrapping it earlier. And again, this one is 33 to 55-ish. The problem here, though, is this is a normal distribution. So sampling distributions tend to be more normal. And so this one is relatively normal. It gives me a smaller confidence interval than this problem was looking for. So to do a t-distribution here, I would need to know a few things. What's the mean of that set of data, the original 11 numbers? What's the standard deviation of that original set? Oops, over here, original set of 11 numbers. And then I have to apply the central limit theorem, there we go, which says you got to modify the standard deviation by dividing by the square root of n. So I take the sample standard deviation, which can be calculated in StatKey or in a spreadsheet, divide by the square root of 11. So I get 0.48878. Now here I use the theoretical normal, so I'm still doing the problem wrong. Notice it's about 33 to 56 this time, which is close to what the bootstrap one was. But I'm still approaching it incorrectly because I'm using a normal instead of a t. So finally I say, okay, I better use a t now. To use a t-distribution, you can't get the lower and upper bounds directly. You first have to find the t-score. And we did this in a spreadsheet in the last few days in the recordings, but here I'm doing it in StatKey. So I went to the StatKey theoretical distribution t. I'll show you that in a sec. And I plugged in my 98% confidence level, and StatKey says, oh, the right t-score to use here would be 2.764. Then according to the central limit theorem and that margin of error formula that was given at the beginning of the problem, to get the margin of error, I take the appropriate t-score from the confidence level, multiply by the sample standard deviation, and then divide by the square root of the sample size. So once I put all that together from my t-dist, I get a margin of error of about 13.5. So then we have to take that away from the mean, and then we have to add that to the mean. So notice now I get a much wider interval than before. So this one is 34 to 58 instead of the other intervals I was getting, which were like 33 to 55, 56. And a t-distribution is always going to be a little bit wider. Okay. So if you accidentally approach this problem or a similar problem by applying the normal technique, then you'll get a narrower interval than what is expected in the system, because I programmed the system to use a t, which will always be wider. It'll have the same center. It's still 44.664, but a wider center. So, and then just at the end here, I compare a t-score here. The t-score for 98% in the middle is 2.764, The z-score for a normal distribution for 98% in the middle is 2.327. Notice how much smaller the z-score is than the t. And for the same middle percent, the t-score is always going to be bigger than the normal. So how did I get that? Let's switch tabs here. Come on. Sorry, my Zoom menu is in the way. So to get the t-score, I did it in StatKey. Yeah, degrees of freedom are, it's always one less than the sample size. So I go down to theoretical t. I had a sample size of 11, so I would say degrees of freedom is 10. It's always one smaller. And then to get the t-score, you just put in your confidence level in the middle here. So that would be the 0.98 for the problem I got. And there's that t-score of 2.764. And the other side is always going to be the opposite of that. We just want the positive version for that. And I can do this in a spreadsheet also. So let's bring that up too, just for fun. Get my drive. And spreadsheet I've been playing with this week. Looks like I didn't do this one yet. What's there? Mean dogs. All right, here's one I can use. So this is review number 8. And I'm supposed to use a t distribution for this one. And I was given temperatures. And you could also use one of the pre-built spreadsheets that I put up back. Let's see. And hopefully you have these stored on your computer or in your Google Drive so you can get to them quicker. So let's see, I should have one of them here. Confidence interval for a mean. So that would be this sheet here. So you could use the pre-built, and the first tab is t interval, so make sure you pick the right tab. Are you doing a t or are you doing a z? In this case, we'd be doing a t. And then I could enter my sample data here, and then the computer will calculate the numbers I need here, and I would have to enter my confidence level there. But I just want to, all I want to do right now is just double check that t-score. So to get the t-score for a confidence level of 98%, we need to know what alpha over 2 is, right? The tail probability, alpha over 2. So it's a little more work in a spreadsheet. So to get that, first I have to go 1 minus the confidence level to get alpha, and then I can cut that in half, and the parentheses are important. So that puts 1% in the tail, which is right. And so then the t-score that goes with that comes from using the t inverse. So t.inv. Yep. And then tail probability, and then degrees of freedom 10. And it's going to give me the -1, negative 2.764-ish. I just ignore the negative or go in there and get rid of it by making it a double negative. So that was the t-score that StatKey gave me also. Okay, so just to try and help and clarify when you should choose a t versus choosing a normal distribution, and sometimes I just tell you in the problem, and other times you gotta kinda, it's up to you to figure it out. And again, the way you figure that out is what's the given information? Do you know the population standard deviation or not? Is the sample size small or not? Is there a proportion or not? So those are what help us decide on a normal versus a t. Okay, what else should we do? Do any of you have some other questions you wanted to take a look at, or you just want me to pick something? Application 8, okie doke. Let's see what we got there. Certainly. So I'm going to leave the review section here and go into the next set. And I can't remember which one 8 was. I do remember somebody asking about it earlier this week. All right, So this is the one that's all one big page, but there are headings above each section saying, hey, use these formulas in this region. 5, 6, 7, 8. Okay, so in 8, our hypothesis test, and we're either using a t-dist, which means we have a mean we're testing, or we're using a normal dist, which means we're testing a proportion. And this one, number 8, is people who own cats. Okay. So I already did this version, so I'm gonna do a similar one. And every time you bring this up, it's gonna be a little bit different. So sometimes it's the proportion of people who own cats is less than some percent, or the proportion who own cats is more than some percent, or significantly different. So you're either gonna get a left tail, a right tail, or a two tail. So number 8 is a question that's worth doing more than once because it'll be a very different test each time. I was given here, let's see, test the claim that the proportion of people who own cats is significantly different, which means not equal. So this is a two-tailed test. So this is a two-tailed test I find to be a little bit harder than other ones. So let's see, I'm gonna narrow my screen for a sec and then copy this. And interesting, why did it fill that in there? So this should be a new problem. Anyway. I'm going to screenshot this part here into a new page. All right, so let's figure this out. And I guess I will, oops, I distorted that. I'll split this recording later since I forgot to start and stop, or vice versa. All right, so test the claim that a proportion. Okay, so right away, I'm on a piece of paper saying, oh, proportion. Okay, so that means I've got a P, not a mu. So any of these that are mu's, not relevant to this problem. Significantly different. All right, so significantly different, that's not more than, that's not less than, that's just different, not equal. So that's a not equal. So since this isn't an equal sign, right, or a less than or equal to or a greater than or equal to, this must be my alternative hypothesis. So a null hypothesis has to have an equal sign in it. So that means equal to, greater than or equal to, or less than or equal to. An alternative cannot have an equals, which means strictly less than, strictly greater than, or just not equal. And it looks like this is the only option that fits what I have. So not equal is significantly different, which tells me I'm going to have to do a two-tail test. So starting my sketch for this, which I usually do pretty close to the beginning of trying to figure out a problem. Since this is a hypothesis test, we put the population, the null hypothesis, in the middle. So 10% goes in the middle, and that's known as P. And then we need more information to figure out what the standard deviation. So what does it mean here to be 1, 2, or 3 standard deviations on either side? All right, so now we're going to look back and see what else they tell us about this problem. So that's about all I can draw based on what I have here. Oh, and let's see, 10% at the, oh, we also have a 10% significance level. So I should note that this right here is my alpha significance level. And since this is a two-tail test, I have to cut alpha in half. So alpha over 2 would be 10% divided by 2, which is going to be 5%. So then that's probably going to be about here-ish. Because the central limit theorem, sorry, the empirical rule says that about 95% of the data is within 2 standard deviations. Oh, that would be 2.5% in the tails. I drew those in the wrong spot. So these are probably going to be more like here-ish. In between 1 and 2 standard deviations on each side. So this over here is my 5% in the upper part because it's a two-tail, and then this would be my 5% in the lower part. And so those two together are the alpha because it's a two-tail. So that's one thing that makes this a little harder. All right, so the next thing we need to know is the based on the sample here, and I don't know what that number is doing there. screenshot this right here, current page. Come on, there you go. Let's blow that up a little bit. So this is our sample information. Whoa. Yeah, let's squeeze that in right there. So what are they telling me here? Let's stick with green maybe. So this right here, that 6%, that's what we call P prime or P hat. That's the sample proportion. And they're saying P prime is 6%. So I'm going to state that as a decimal. Sample size, they're telling me that N is equal to 700. And I'm going to stick with the central limit theorem here in the spreadsheet, but I could do it in StatKey too. I have enough information to use multiple pages on StatKey. So what do we need next? Next, we need the standard error for a proportion. And in a hypothesis test, so hypothesis test for a proportion, the standard error is the square root of P from the null times Q divided by N, all inside the square root. And remember, Q is always 1 minus P. So in this case, that would be 1 minus 10%, which would be 90%. So the standard error for this situation, which is how far a single standard deviation is on the graph, the standard error is going to be the square root. So we need a calculator or a spreadsheet. 0.1 for the 10% times the 90% of people that don't own cats, and then divide by the 700. And again, all that is inside the square root. And we could use the pre-built spreadsheet for this, or we could start from scratch. So I think I'm going to go with the pre-built one. And where's my copy of that one? Let's see. Copy of hypothesis test. I think this is the one I want. And then I want to switch over to the proportion test, because this is a proportion. Then I enter my information. So I have 0.1, 10% is what we think the population is. And then this is again 0.1, but I should have a not equal there. And let's see, I'm just going to type not equal. It's easier than finding the symbol. Okay, my significance level, that was 10%. And it doesn't use that actually in this sheet. Okay, and so then they want to know X and N. Well, I wasn't given X, that would be the 6% of 700. So I think I'll go edit this now, equals 0.06, or you could just type 6% times 700. All right, so 42 goes here, and 700 goes here. So there's the 6% for the sample proportion. And then here they give me that standard deviation, which is about 1%. So now I can improve my graph by using that to label the axis. So let me do that before I do the p-value. So that means this right here. So the standard error is approximately, to 2 decimal places, 1%. So that's 10% there. So this would be about 11% there, and about 12% there. Going the other way, subtracting 1%, this would be about 9% and 8% and 7%. My sample was 6%, which is way out here. So right around here, I think would be about 6%. And so the p-value is going to be this tail, but then I have to reflect that over to the other side. So that's about 4 standard deviations. So on the other side, there's going to be the reflection of that, because it's a 2 tail. So whatever number that ends up being, it looks like it's going to be about 14%. I need that probability too. So I need this number here and that number there for the p-value. So the p-value is, that's supposed to say is both tails. Even though my data gives me one, I have to reflect to get the other one. So basically we just double the left tail is another way to do it. All right, so back to the spreadsheet. And I believe this spreadsheet calculates for you the left tail, the right tail, and what if it was two tails. So notice the left tail is 0.0. Let's pull that up a little more. Oops, come on. There we go. The left tail is 0.0002, and if we double that, we get the two-tail version. So this is the p-value for this situation. Notice it's really small because my sample is way out on the left. And even though we only have one sample that puts it on the left, we did choose a two-tail based on the given information, so we do have to double that left tail. And that's what people usually miss, that part right here. My test statistic is the z-score. So given that we were expecting 10% of people to own cats, right? That's the null hypothesis. And we have a sample size of 700. That's what leads to this standard deviation here, which is also the standard error. I get a z-score, which means we are about 3.5 standard deviations to the left of 10%. 3 standard deviations is way out there. Most data is within 2 standard deviations in a normal distribution. So this is an unusual event. It's definitely, the p-value is way less than 10%, right? We're at, oops, if we change that to a percentage here, we're at 0.04%, right? So that's a wicked small p-value. So what do? Reject the null or fail to reject here, given that we have a wicked small p-value?
Reject the null, right?
Absolutely reject the null. Yeah, the p-value is way smaller than the significance level, which means that if this is a good sample, something is wrong with the null hypothesis, that the claim of 10% is wrong. 6% is far enough away to say, not right. Okay, so back to my sketch. And so we'll write up a conclusion here too, because that's good practice. So my p-value, both tails, so this tail had a probability of 0.0002-ish, and this tail then has to be 0.0002. So altogether, the p-value is 0.0004, which comes out to be, changing that to a percent, 0.04 or 0.04% is again this p-value. And because it is so small, that implies we reject the null. Oops. All right, so now we get to state what it means to reject the null in this case, and then I'll also give an interpretation of what that p-value means. So those are two different things related to this problem. So the reject the null is the decision, and let's see, this problem I think just asked for a decision, not a conclusion. Yeah, so the p-value 0.0004-ish, and we reject the null. This is a two-tail. P is not equal to 10%, significantly different, again, means not equal to. So let's just get some green lights on that one. Woohoo. Okay, so next I'm gonna write up what I think the conclusion should be and what the p-value means. How would I interpret what that 0.0004 means? And again, I could do this in StatKey. To do this in StatKey, I have two options. And maybe I should show that quick. Where's my notebook? To do this in StatKey, we need to know the null hypothesis, we need to know the sample proportion, and we need to know that standard error. So all of those have to be given and or calculated to use StatKey. So if I were going to do StatKey, come here, show desktop. Which one was I on here? Normal T distribution. So one, I could use a normal distribution, in which case I would enter in my null hypothesis, which is 10%. Oops, yeah, I know I need to calculate the standard error. The standard error would be that square root. So I'm just going to whip out a Google calculator. So the square root of 10% times 90%, whoa, divided by 700 is the formula for the standard error of a proportion. So I'm just going to copy that and stick it in stat key. It's one nice thing about the Google calculator or a spreadsheet. You can just copy numbers from one place and stick them somewhere else. So that goes here. This is a two-tail test, and then I enter the sample proportion, which was the 6%, and since 6 is smaller than 10%, it goes on this side, not that side. That would screw shit up. So here I go 0.06, and it says, notice that's the same number the spreadsheet gave me. And so I would add these two numbers together because it's a two-tail test. So that's one way to do this in StatKey. The other way to do this in StatKey for a proportion, and if this is too many options, then just block your ears. This is I could use the randomization test for a single proportion. And in this case, I have to go set the null hypothesis, and then I have to set the sample data, and that was a count of 42 out of 700 is what we figured. And then over here, that should show me the 6% if I did it right. And then I just start generating thousands of samples. And this should give me about the same answer for a two-tail, but I still have to come down here and enter my sample number, 0.06. And the simulation got it a wee bit smaller. This one says 0.0001 instead of 2. Interesting. So I'm going to try it again. These will be a little bit different each time. Two-tail. Came out to 0 that time. So yeah, so the simulation doesn't always agree with the central limit theorem, which is the other two ways I did it. If you do something like this on a test, just be sure to tell me how you got your answers, so that way I can look back at it and figure out if you did it right. So if somebody showed me this, I would say, yeah, okay, that's close enough. Even though it's not exactly what I was expecting based on the other way of doing it. All right, conclusion time. Let's see, new page. Come on, there we go. So what does it mean to reject the null? Oh, my pen's being glitchy. In this situation. So let's just go back and read the situation again. Test the claim that the proportion of people who own cats is significantly different than 10%. So that was my alternative hypothesis. The null would be that the proportion of people who own cats is 10%. So we have sufficient evidence that it is different than 10% is what we have here. So that's what I'm going to say. Oops, wrong button. That button. Okay. So we have sufficient evidence and I'm not going to state I'm rejecting the null and accepting the alternative. I'm just going to state what the alternative is, what I have evidence of. We have sufficient evidence that my parameter, the proportion of people who own cats, is not 10%. Right? I could say significantly different there, but my mom would like is not 10%, right? It means the same thing, but it's slightly plainer language. I do need to do the sufficient evidence thing, and she might say, well, what do you mean you have sufficient evidence? Well, then I would have to state my p-value and state what it means, because the p-value is the evidence here. But this right here, that's it. That's my conclusion. As simple as I can put it. What does the p-value mean? That is what's significant. So my mom says, well, what do you mean significant evidence? So now I'd have to try to explain the p-value. So here goes. So what does this p-value mean? And because this is a two-tail, it's a much harder thing to explain than a left tail or a right tail. So I got to kind of look back at my graph to get a handle on that. Let's see, which I think the stat key graph here will be more helpful. All right, so since my data was 6%, but this is a two-tail test, I have to reflect that to the other side, and StatKey does that for me, and StatKey says it's about 14%, which is what I was guessing earlier. And again, that's based on the mean of 10% from the null and the standard error, which is that funky formula with the square root of PQ over N. All right, so 6% is the low, 14% is the high. So I need those two numbers to make this interpretation of the p-value. So again, what I'm doing is an interpretation of the p-value here. So there is a 0.04% chance of finding another sample, and I should state the sample size because that matters, right? That's part of the standard error. Another sample of 700 people. Okay, so there's a 400% chance of finding another sample of 700 people for which let's go with percent. The percent of people who own cats is either less than that 6%, or it could be more than 14%, that reflection. When we were expecting to find about 10%. And that's that null hypothesis in the middle. Who own cats. All right, let me read that, make sure I got it right. There is a 400% chance of finding another sample of 700 people for which the percent of people who own cats is less than 6% or more than 14%. And the general description of the p-value in the text says more extreme than the sample data. And so I'm just being more specific about what it means to be more extreme, less than 6% or more than 14%. So you have to describe what your tails are. Is it a single tail on the left, a single tail on the right, or is it two tails? That has to be in the interpretation. So just a reminder, this is an interpretation of a p-value. What does it mean in this situation, given the thing we're trying to measure here? And I think each of the past 4 days before this, I did a problem like this where I gave both my conclusion and my interpretation of the p-value. So if you look back in the playlist, the last set of, I don't know, I think I made like 12 videos this week already, ranging from 10 minutes to half an hour on these kinds of problems. Anyone that says hypothesis test in the description will have something like this in there. So, all right, I'm going to stop this recording here. I think I've thoroughly abused this problem.